Good morning, Astronomy 1020. Welcome back to part 2 of lecture 11, where we're covering the topics of special relativity and general relativity, proposed by none other than good old Albert Einstein himself. Today, we explore more of the consequences of Einstein's two postulates of special relativity. Why don't we kick things off by having you guys remind me, everyone who might have missed Tuesday's class, what are the two postulates of special relativity? Does anyone know what
It's the law of physics are the same in all inertial reference frames, and then the speed of light c is the same for all observers regardless of velocity.
Excellent, Mariah. And these two seemingly innocuous statements, especially the second one, break the Galilean transformation of velocities. You guys remember that technical term, the Galilean transformation of velocities? It means the speed of the skateboard plus the speed of the ball is the speed the outside observer will see, right? Especially it becomes bizarre when you enter what is known to physicists as the relativistic regime. The relativistic regime is where velocities become a high enough fraction of the speed of light that you start to notice wacky effects. Let's take some notes on this because I think I've got some stuff that will help here, okay? So for special relativity, first proposed in 1905, Albert Einstein began with his two postulates of special relativity, the ones that Mariah just read to us. And it turns out that if you assume these two things are true, there are a number of consequences that result that mean we have to change the way we think about distances and times and a bunch of other things as well. Physicists refer to this as the consequences of special relativity. And I spent a great deal of time taking us through our first consequence of special relativity, a sort of wiggy little formula known as time dilation. Today, where we clean up special relativity, I will introduce you to some other consequences of special relativity. Why don't you guys look up that formula and read it back to me, okay? We derived that in our labs. I get the glare gone here. Sorry, I needed the glare be gone. Let's look up that formula for time dilation. What did it look like anyways?
Is it TA equals TB over the square root of 1 minus V over C squared, yeah.
Right. Where V over C is your percentage of the speed of light. That's a really important trick for my intro students. A mistake that I've seen a lot of students make before is sometimes I'll give you a velocity like, say, 50% of the speed of light. And I'll see people do silly things like try to do 0.5 over C, forgetting that the velocity itself is 50% C. Do you see what I mean? So what goes in the parentheses there is just the 0.5, not 0.5 over C. You got to watch out. It's actually 0.5 C over C. The velocity divided by C is your percentage of the speed of light. In fact, sometimes to make this even more explicit, in a more advanced textbook, they will actually replace V over C with a term called beta, the rapidity. And beta is supposed to be how fast am I going as a percentage of the speed of light. Sometimes it makes the formula look a little less threatening, okay? So for instance, I could define beta as V over C, and then it's assumed that beta is 0.5. You know what I mean? And that lets me kind of rewrite this formula, 1 minus beta squared. That's not a necessary step, but it helps if you have to write the equation a bunch of times, okay? Did everyone feel okay with that, or was that a little too scary and advanced for you? I don't know. I would rather write beta than V over C every time personally. Okay, I'm gonna play one more math trick like this. By the way, can you remind me, Vladimir, who was TA and who was TB in our little fairy tale? Here, a
So
slideshow might be helpful for students. Wait a sec. Before you answer that question, let's find a picture of time dilation. Okay, here's a crappy little image showing us our two observers. Who is TA and who is TB?
so from what I remember, TA is TA should be the one observer in how do you even word it?
Okay, let me help you,
The
Vladimir.
time
There was an
time for the
observer.
inertia. Huh?
There was an observer on the train platform, and then there was an observer on the moving train.
Yeah.
Who
So
is TA?
TB is TA is the observer on the platform.
Correct. And TB must be in the train, right? So in
Yes.
this little cartoon here, this is the laser beam as seen according to observer B, right? And this is how the laser beam travels according to observer A. You have to remember what we were doing that to understand this, right?
Yeah.
It's customary in physics, and I said this last time, but I'm gonna say it again. Instead of calling the observers A and B, because it can get a little bit confusing who's moving and who's at rest, it's customary to call T the observer time, that's the scientist on Earth, and to refer to this time as the rest time. Now, that's going to sound pretty strange to students, because if you remember, this was the guy who was actually in the train. Do any of you have a sophisticated enough understanding of relativity to explain to me in the class why B is actually the rest time and not the moving time?
Because B can successfully claim that they are at rest and the observer is moving, and they're also not aware that they're moving too.
So that is correct, and that is a part of this story, Vladimir. So that's relevant here. But there's a more important reason. So, but see, Vladimir, I could flip that around on you and I could say TA can also claim that they're at rest and TB is moving. Why do we designate TB the rest time?
Because that's where the event is taking place.
And notice his classy use of physics terminology. That is the frame in which the event takes place, and the event is a charged word. Nicely done, Vladimir. Okay, so this is the frame. Let's keep it as simple as possible of the event. Here's the thing about the event, Vladimir. Sometimes it can be really confusing, and sometimes it's not even implied what the event is. You have to figure it out. That's where you can get into these paradoxes. Okay, you guys agree with me that this time and this time are times, and they could be measured in any units: seconds, hours, days, years. It turns out then that all of the relativity, the wacky relativity effects, get contained in a factor 1 divided by the square root of 1 minus the speed squared, okay? Allow me to do, and I know students hate this kind of shit, a change of variables, okay? I'm going to introduce a new term, and it's a magical term. They don't do this in your book. This is a little extra sprinkled dust that I'm giving to you guys, okay? It's called the boost, okay? Let me introduce to you the boost. And the boost, a term gamma, can be considered your special relativity whack factor. It is the factor by which things are whacked out in relativity. And it's defined, notice my use of triple equals, it is defined in the following way. 1 divided by the square root of 1 minus v over c squared. Now, I could have put beta there too, but I'm worried that you'll forget about the beta thing. So that's what I'm going back to b over c squared. Here's the deal with the boost, my lovely friends. Every single consequence of relativity, every whack factor, ultimately has a factor of the boost in it. If you're willing to work in terms of the boost, you only have to punch it into your calculator once, and then you can just kind of think about the time dilation and some of the other stuff without worrying about the calculator mistakes. You're going to have to just trust me on this for a few seconds, and then you'll see the wisdom of it, okay? Now, here's the deal with the boost. The boost must be 1 or greater. It can never be less than 1. So how do we say this? The domain of gamma is a number that is okay, greater than or equal to 1 all the way to infinity. Okay? So gamma can be 1 or any number higher than that. When the velocities are low, gamma is approximately 1. And as you get more close to the speed of light, gamma goes to infinity. I guess we could do that. Gamma is a number between 1 and infinity, okay? Okay, right now you're feeling a little uncomfortable. You're thinking, why are you doing this to me? I don't see the usefulness of this. I understand that. Let us now rewrite. Actually, let's see if you guys have the chops. Vladimir is planning on studying applied math. Let's see if we can get some help from him. Vladimir, could you help me rewrite time dilation in terms of the boost? What would time dilation look like now? You're muted, buddy. You're muted.
T rest times gamma.
That's right. The observer time is now gamma times T rest. Do you guys see how much cleaner the equation is? Do you see that? That's time dilation. You can call this time dilation. I'm going to start putting things in terms of the boost. Last class, we actually worked out a problem where there was a train car with a laser beam in it, and the laser beam took 2 seconds. I think we were traveling at maybe 80% the speed of light, or was it 85%? I can't remember.
It was 80.
80%. Why don't we all try to work out the boost for a speed of 80% the speed of light? I'm going to need to erase here. Do you guys have all this in your notes? This is critical stuff. Andy, do you need a second?
No, I got it.
All right, cool. I'm trying not to go too quickly, but I should speed up here. Okay, as an example, find the boost for a velocity of 80% the speed of light. So our equation would be 1 divided by radical 1 minus 0.8 squared. I showed you guys how to do this last time using your reciprocal key. Why don't you see if you can punch it in first? By the way, I am going to have you use the boost on the final exam, and the goal is to make the problem easier for you, not harder for you. You're going to have to trust me a little bit, okay? So could you guys see if you can handle that calculation? I want to see if you can do it without my help first. There's a lot of places to make mistakes in this computation, but you can get pretty damn good at it. Mariah, Tegan, Mateus, Andrew, Vladimir. Shout at me.
5/3.
Okay, that's cute. How about as a
I just didn't like the decimal. That's the exact answer.
Is that 5/3? Damn, you're good. I wish I studied mathematics in Russia. Okay, you're right. Look, shit. So I was gonna say 1.7, but yeah,
Yep, it is 5/3.
it's 5/3. Nice. Vladimir, I was secretly bad as a kid at fractions, and so I'm a little self-conscious here. Nice. Okay. Did it just in case anyone at home in the television studio audience is struggling with that? I want to show how those of you who successfully did how I would have done it. Okay, so clear out. Remember, my goal is I do the inside first, then I square root, then I reciprocal. Okay, so watch me quick. 1 minus 0.8 square key equals shift square root shift 1 over x. Hopefully that wasn't too quick for you, okay? Everyone give that one more shot if you failed the first time. You can learn to calculate the boost quite quickly, and then relativity becomes fun to think about, okay? Let me just do one more thing for those mathematically inclined. I want to see if I can find a graph of the boost. Sometimes it's possible to do this. So plot of the boost special relativity. Sometimes you can, and I want to, there is a graph for this. I did download it at one point. This is kind of it, but there's a better one. I did download the graph at one point, but at this point, it's going to be faster for me to poke around on the. They also call it the gamma factor. Come on, what the hell? Okay, so let's just do the boost relativity. I think they have a Wikipedia page. Oh, the Lorenz transformation. Okay, that's another term for this. What I want to find is they do have a plot of this, and I'm really kicking myself that I didn't. I have like 5 or 6 different repositories of physics pictures, and I'm just worried. Come on. Okay, here it is. Here it is. This isn't a great graph, but it will do. Okay. I don't love it. Actually, this is the one that I want. Yes. Okay. This is the graph that I want. Forgive me. This plot shows us control minus, let's get back to 100% or so. Bear with me here, guys. On the y-axis, you have the boost. And on the x-axis, you have your beta factor, your percentage of the speed of light. Notice that up to about 20% the speed of light, gamma is relatively indistinguishable from 1. In other words, you don't really notice any time dilation at slow velocities. Above 20%, we call this the relativistic regime, okay? And the relativistic regime is where an average human would start to notice discrepancies in time dilation and other effects that I'm about to describe. So notice that as you get closer and closer to the speed of light, gamma goes all the way to infinity. Let's try a couple of quick examples with this, okay? And this is designed to improve your quality at special relativity before we go forward. Okay, let's say a professor, a hypothetical professor, not related to anyone present in the room, drives to CCR. I'm sorry, guys, there are gangsters in my neighborhood who are pumping reggaeton, so it's getting harder for me to concentrate in special relativity. Okay, so a professor drives to CCRI at 95 miles per hour, okay? And meanwhile, in this completely hypothetical situation, there are students who are sitting patiently in the classroom waiting for the lecture to begin, okay? Now, let's say that the professor in his van, okay, is traveling at 95 miles per hour, and it typically takes the professor 20 minutes to get to CCRI. How long will the students have to wait due to the effects of time dilation? How should we begin this problem? Well, let's write the question down. How long does the trip take in the student's classroom frame? We can do this with the boost, or we can do it without the boost. I suggest the boost.
So we have to convert 95 miles per hour into percentage of the speed of light.
True. So why don't we cheat a little, Vladimir, because you know that the imperial unit system is just total dog shit. So what I'm going to do is, instead of doing the calculations, I'm just going to type into Google 95 mph
59
meters per second.
meters per second.
We'll just start there, right? So 42.5 meters per second, okay? So what percentage of the speed, so let's calculate our beta term first. Our beta is V over C, which is 42.5 meters per second. What's the speed of light in meters per second, class?
3 times 10 to the 8th.
3 times 10 to the 8 meters per second. Let's see if I can do it faster than you. 42.5 divided by 3 exp 8. I get 1.4 times 10 to the minus 7. Okay, let's see if we can calculate the boost on this. This is going to be pretty tricky. The boost is this 1 over the square root of 1 minus 1.4 times 10 to the negative second squared. Negative 7 squared. Sorry about that. This could be tricky to do on our calculators. Let's try it together. Actually, 42.5 divided by 3 exp 8. So here's my doodah. Watch my moves here. I'm going to square my doodah.
Oh, that's still a problem.
Sorry. I'm going to square it. Then I'm going to negative it. And then I'm going to add 1. That's my goofy way. Oh, wow. It can't even handle it, right? Because if you do 1, if you do 1 minus 1.4 exp negative second squared, it's so close to 1 that your calculator can't handle it. I actually have tricks for how we can do this. We'll have to do it in our mind, though. Basically, this is 1 divided by the square root of 1 minus 2 times 10 to the negative 14, right? Want to see the trick I invented to figure out how to do this? What if I had 1 minus 2 exp negative 3? I would get 0.998, right? I guess that if I do 1 minus 2 exp minus 4, I'm going to get 999, and the 4th place will be an 8. Ready? So 1 minus 2 exp negative 4. Sure enough, it's 0.9998. So I could easily replace that with 0.999. Now I'd have to have 13 9s, and the 14th one would be an 8, right? So I'd have 999, 999, 999. That's 9, 10, 11, 12, 13, 14. Of course, if you square root that, well, let's try this. If I have 0.9998 and I square root it, whew, well, it just gets stupidly closer to 1. You know what? Who cares? Gamma is 1. What does that mean, class?
That there are no differences in the time for students. They'll wait 20 minutes.
By the way, as a test of your knowledge of relativity, Vladimir, let's hypothetically say there was. Would the professor's 20 minutes be T rest or T?
Okay.
That's the tricky part to relativity, is figuring out who's the rest time.
Okay. I believe the professor is T rest.
Exactly, because the professor is in the so-called, the students are the scientist observers.
Is the kind of the event.
Yeah, what's the event is the time in the professor's frame. That's how we're taking this approach, okay? This is a classic example of how relativity can get confusing, because when you say it takes 20 minutes from the professor, you don't know if that means, is the professor the observer of 20 minutes, or is the professor saying it's 20 minutes elapsing in my own frame? In this case, you presume that I am the one timing myself to CCRI, so I would be the rest observer. Very good, Vladimir. Okay. What if I could travel at the speed of light to CCRI?
So that would be 1 over 0, but then if you take the limit of it, it goes to infinity.
Correct, but hold on, Vladimir. They might not be as quick as you on the math stuff. Let me erase this, okay, students. And let me just explain to you what Vladimir was doing. Suppose the velocity was boosted up to the speed of light. It's good for you guys to think about this for a second, okay? The beta factor now, V over C, would be C over C, which is 1. So far, so good, right? Now watch what happens with your boost. As Vladimir suggested, radical 1 minus 1 squared. 1 squared is 1. 1 minus 1 is 0. And you end up with radical 1 over radical 0, which is 1 over 0. Now, when you took your baby high school mathematics class, Mariah, what did your teacher say about 1 over 0?
I think something like undefined.
Yeah, that's because your high school math teacher wasn't actually good at math.
Okay.
Sorry. Okay, so more properly, when you divide by an arbitrarily small number, your number gets bigger and bigger. And as Vladimir said, using some advanced terminology, in the limit, as the denominator approaches 0, the quotient goes to infinity. So 1 over 0 is technically at infinity. That's how we're supposed to think about this, okay? So what does it mean, a gamma of infinity? Let's plug in a gamma of infinity into our time dilation formula. Now, someone besides Vladimir, see if you can handle working with infinity, okay? If the observers, the students, is equal to infinity times the rest time of 20 minutes, infinity times 20 minutes is still infinity. Wait a minute, something went wrong here. What did I do wrong? It's very easy to get yourself screwed up. I wanted to basically, if the professor travels at the speed of light, the trip should be relatively instantaneous, right? From an outside frame. What am I doing wrong? Guys, I screwed up somewhere. I know I did. And I'm just not sure where.
Things always go wrong when you work with infinities.
Huh?
Things always go wrong when you work with infinities.
Yes, but I've done this problem before and I've not screwed it up. I'm just... I think it's... Okay, here's the deal. It's goofy. Oh, I know why. If I'm traveling at the speed of light, it should not take 20 minutes to get to CCRI. That's the first thing, right?
That's right.
That's the first thing I did wrong. I'd have to calculate the distance to CCRI, figure out what that fraction of a time was. But here, I know, okay, guys, I know what I did wrong, okay? I know exactly what I did wrong. Basically, it can't take 20 minutes.
That would be 51,000 meters. So
What
like
is?
your velocity 42.5 meters times the time. No?
Oh, that's a good way to do it. So if you're assuming...
I mean, I just kind of assumed it's a line.
So what's the distance to CCRI?
51,000 meters.
It can't be 50 kilometers from Providence to...
Yeah, but like, that's because I assumed that it's a straight line and you did not ever stop. So
Right. Okay. Here's how we can do it. Google Maps has it. We're getting a little off track here. So let's do 90 Eddy Street, Providence, Rhode Island to what is it? 400 East Avenue. Warwick,
That's
Rhode
it. We
Island.
know that's it. We know where you live.
Yeah, it's okay.
I'm taking a
Come and get,
screenshot.
come and, there's already enough crazy people down here. I'm not afraid of a few more. Okay, you guys will actually seem sane compared to most of the people on the street. Okay, so it says 10 miles, right? So 10 miles, sorry, 10 miles to, let's do kilometers. Is it really 16 kilometers to CCRI? That's crazy. Okay, so 16 kilometers. Let's go down here. I know exactly how I screwed this up, and even though it's taking a second, I want to fix it. Okay, I want to fix it. Oof, size large. Okay, so if
Oh,
this,
what did you write at the top?
oh, I just wrote that the distance to CCRI was 16 kilometers.
All right.
Okay, here's the. Can I tell you where I screwed up and why the question didn't make sense the way I phrased it? I cannot choose 20 minutes to be the professor time if I'm traveling at the speed of light. In fact, the only way to pose this question is, according to the students, if it takes some number of minutes or hours for me to get there at the speed of light, how long will the trip take from the professor's point of view? You have to calculate the rest time, not the observer time. Trust me on this, okay? So if we know that I'm traveling at the speed of light, 300,000 kilometers per second, and we know that I'm traveling a distance of 16 kilometers, how many seconds should it take me to get to school? If I could travel at the speed of light, it's going to be a wicked short time, right? I get 5 times 10 to the minus 5 seconds. So the student's perspective, if I could punch my van up to the speed of light, the trip would take 5 times 10 to the minus 5 seconds. And that is actually the observer time. How much time would elapse inside the van? Are you guys following me, or have I just blown past you on a speed of light ride?
I'm a little lost.
Well, all right. So are you lost on this part, or are you lost on the 5 times 10 to the minus 5 seconds?
In the top part, the t equals infinity times rest.
All right. And the reason you're lost is because I initially did a bad job explaining this. That's not your fault, Maya. It's mine. Okay.
Okay.
Let's say you're with me on the 5 times 10 to the minus 5 seconds. That made sense because you know distance equals rate times time, right? Okay.
Yeah.
Andy, can I erase this little bit at the bottom? Earth to Andy. Can I erase that?
Yeah, you can erase it.
Because would it just be that equals infinity times t rest and then?
Yes. I'm trying to get you to think slow and careful about this. Did you follow me? Let's make sure each one of these components makes sense, and then I'll explain this, Mariah. Okay. You understood the 5 times 10 to the minus 5 seconds, because that's just how long it would take a photon to get from my house to CCRI, correct?
Mm-hmm.
Did you understand the infinity when we calculated the boost and we got infinity?
Yeah.
Okay. So let me explain the last part. Inside the van, that is the rest time. We're trying to imagine that instead of a laser beam, it's, say, my heartbeat. It's the flow of time from me, a biological organism's perspective. It was easy enough to calculate the time for a photon to get to the classroom because we know distance equals rate times time. The phrasing of the question means how much time will have elapsed for the professor inside the van. Now you've got this equation, this times infinity equals that. Let's solve for t rest. 5 times 10 to the minus 5 seconds divided by infinity equals t rest. What number do you get, Mariah, when you divide by infinity?
Is it infinity?
No.
I don't know then.
Well, here, if you don't know, try to imagine a stupid huge number which is not quite infinity, but is still big. 5 exp minus 5, right? And let's divide it by the biggest number we can in our calculator, 99999999999. What do you get?
Basically 5.
No, basically fucking 0. That's 10 to the minus power of 15. Hey, listen, guys, I can't tell you this enough. That's not the number, okay? This is the number. The power of 10 is the number. Not basically 5, basically 0. If you divide by an arbitrarily large number, your result will be arbitrarily small. 0 seconds. What the hell does that mean?
That means that from the perspective of a person who travels at the speed of light, the whole universe is kind of like a point.
Very good. It's not a point because it's actually more like a sheet. Right? What's a vector problem, Vladimir? If you're traveling in a straight line, the universe will collapse like this. It's a sheet, not a point. But very good. See, he made two loops that, well, okay. If you are in the van's frame, to travel from my house to CCRI would be an instantaneous journey. But actually, it also follows that wherever you were traveling, it would be instantaneous. Even if I were to travel to the Andromeda Galaxy in my van at the speed of light, the trip would take 0 seconds. This is one of the reasons physicists believe you cannot actually even achieve the speed of light or beyond it, because you would have some really nutty and buggy consequences. For instance, well, okay, let's explore some of the other consequences before I start riffing on this, okay? Let's reset our notes here. Okay, and let's explore some of the consequences of special relativity. This is how I wanted to start the class today, but I kind of got lost in the sauce for a second. Hold on, guys. I need a freshie. I need a fresh marker. Okay, you've already learned about time dilation. From now on, students, I'm going to phrase everything in terms of the boost because it's more elegant that way. The idea behind time dilation is the observer time is the boost times the rest time. That's our formula. The idea, and you have a little mantra or a phrase to repeat every time you want to understand one of these consequences, is moving clocks run slow. And you have to carefully consider what that means. It means to an outside observer from the classroom frame or the platform frame, the rate of the flow of time within the van or within the train car will be slower than the rate of time outside of it. If I had wanted to, do you guys remember how I did the time dilation derivation with a laser bouncing up and down inside of a train car? I could construct a similarly elaborate scenario to do my next consequence, which is length contraction. I'm not actually going to do that because you saw it took a whole lab period to derive it. But basically, just to give you a sort of sense of how I would set things up, I think I've got a picture somewhere. What I would do is I would imagine a sort of a box car, a train car. So let's go to slide 23. 23. Okay. I would imagine a long rectangular train car. And this time I would attach the laser beam to the edge of the cart. And I would fire the laser forward, bounce it off of a mirror and back. What would happen is as you traveled at faster and faster speeds, closer to the speed of light, it would turn out that the length of the car would need to contract in order to preserve the fact that the laser beam has to travel at the same rate for both observers. You're not going to feel good about that. I would have to set this problem up quite elaborately, but I'm not going to do this. If you perform such a task, and I'll leave it as an exercise to the reader to do this, you would discover that a second consequence of special relativity is an effect that we call length contraction. Moving objects shrink and contract in the direction of motion. And probably the best picture I could show you to kind of show you this effect is to imagine a rocket ship traveling at a variety of velocities from 0 c all the way up to 99.99999% the speed of light. If the rocket ship is not moving, or if you were in the rocket ship's frame, it will have its longest possible length, which is known as the rest length. The rest length is the length of an object when you are in the same inertial reference frame. For instance, the rest length of a meter stick is, wait for it, 1 meter, okay? However, if I could slide this meter stick past you at a velocity close to the speed of light, this meter stick would shrink in the direction of the meter stick only. It would not get squishier. It would not get any thinner. It would only contract along the meter stick's dimension, okay? Let's look at the formula for length contraction in terms of the boost. Length contraction is often expressed using the following phrase or mantra. Moving rods or moving rulers shrink. And the reason why they choose either rods or rulers as an example is they're trying to impress upon you that an object will only shrink in its direction of motion. For instance, in my cartoon slide, notice that my rocket ship does not get any thinner. It only gets shorter along its direction of travel. You see what I'm saying there? Let me be very explicit. This dimension does not change, nor does the thickness of the tube, only the length of the tube, okay? The formula goes like this. The observer length is the rest length divided by gamma, the boost. We're going to be trying some homework problems with this today. In fact, maybe I'll show you one now. Do I have time to F around here? Nope, I don't. Okay. Let's leave it there then. Let's explore some. I was going to do a sample problem called the barn paradox, which is pretty wiggy, but I have to save that. I need to erase this. I'm going to give you some of the other consequences. Actually, I'll squeeze one down here. An even stranger one is something known as mass increase. Believe it or not, the masses of objects, literally how many kilograms they comprise, will change as you travel closer and closer to the speed of light. Mass increase has the same formula as time dilation. The observed mass is the boost times what is known as the rest mass. The rest mass is the mass of objects when you occupy the same reference frame. Moving masses increase. This has one of the lamest mantras, okay? Do you know, have you guys heard of the Large Hadron Collider? You don't know what
that accelerates particles?
Yeah.
I can't see the rest of the screen.
Oh, sorry. Hold on. Let's let you guys grab this stuff. By the way, there's 3 or 4 more consequences of SR that I need to release on you, so we ain't done yet. You got that, Andy?
Yeah, I got it.
All right. I want to show you guys something before I go forward with more consequences. Mariah didn't know about the Large Hadron Collider, and we're going to fix that right now because the Large Hadron Collider is cool. You've probably heard, I hope you've heard of particle smashers before, particle accelerators. Physicists take long magnetic tubes, they take streams of protons and whip them around a giant magnetic tube closest as they can to the speed of light, and they smash them together to make little nuclear explosions and find out what the hell is inside a proton. One of the most powerful on Earth is known as the Large Hadron Collider. Now, Mariah, the first thing I want to do is show you what the inside of it looks like. And if ever there was a pitch for going into physics or science, here it is. Why punch into your crappy little office cube when you could go to work at the Death Star, okay? This is what I want my office to look like, okay? I want to look at this thing when I go to work, not a beige office cube, all right? And this thing is pretty epic. It's a 27-kilometer long track that's on the border of France and Switzerland. It's absolutely huge. And it's this long magnetic tube that basically just whips protons around, smashes them together, and then observes what happens when protons collide. But the question is it even really protons colliding anymore? Let's start by taking a little peek at their Wikipedia page to find out what the percentage of the speed of light they typically get protons up to. Check this out, guys. Where is it here? Oh, look at this. The protons have a Lorenz factor. That's, by the way, you know how I call it the boost? The professional term is the Lorenz factor. The protons in the Large Hadron Collider typically have a boost of 7,000, which means they're traveling at 0.9999999C. That's 99.999999% the speed of light. Okay, think about how stupid that is. You would have time dilation and length contraction of up to a factor of 1,000. That also implies, according to our calculation here, that you're not just colliding two protons anymore, but you're colliding the equivalent rest mass of 7,000 protons. And that makes a hell of a nuclear explosion. All of these crazy subparticles come out, and we now study them as part of what's known as the Standard Model of Physics. The Standard Model of Physics is our current highest theoretical framework for how matter and nature and energy exist. It's a big topic in physics. And basically, it tries to understand what are protons made out of? How do electrons fit into this, and neutrinos, and all these weird particles you might have heard about in a science fiction show. This is the picture. I want this picture. How do I do this picture? Yes, here it is. This is the obligatory Standard Model of Physics picture, where they try to show you the different varieties of quarks that exist, the different variety of leptons, which the most famous is the electron, the various gauge bosons. These are the fields that talk between particles. For instance, photons can be thought of as electromagnetic waves, or they can be thought of as the spider web that connect one charge to another charge and make them tickle each other, okay? There are gluons and Z bosons. And then there's the Higgs boson. This is the particle that imbues other materials with the essence of mass. It's crazy ass stuff. You got to learn a lot of physics before you're ready to contemplate the Standard Model of Physics, but it's interesting. Okay, you guys got this, right? There's probably about 6 consequences of special relativity I want to introduce you to, and then I'm going to jam a little GR down your throats. Okay, one that's going to come up today, which is kind of obscure, but it's going to be in our homeworks today, is something called the failure of simultaneity. Simultaneity means simultaneous things. And I'm going to give you a little cartoon picture to help you figure this out. And the way I would explain it, let me get my handwriting a little better, because that word is complicated. Simultaneity. Simultaneous things. If you have 2 different events and those events occupy different places in space-time, so this is position X and that's position Y or something, if they're separated by some distance, okay, the events could be supernovae, they could be a flash bulb going off, they could be you playing the kazoo, it could be anything. Two events at separate points in space that are simultaneous in one observer's frame, in one inertial reference frame. So if you have two events and those are simultaneous in one inertial reference frame, will not and cannot be simultaneous in a moving inertial reference frame, obviously at relativistic speeds. I'm sorry if that's a little wordy, but I'm not sure how better to put that. Mateus, are you having trouble with my handwriting here?
No, I think I got it.
Okay. I could understand if that sounds confusing. Luckily, I've got a cartoon which I believe will help. Okay?
Wait, can you please give me 1 more second to copy it?
Yes, sure.
All right, thanks.
What you drinking, Tegan?
My sister randomly decided to make milkshakes, so she brought me one.
Damn, I want to be at your house. I'll be studying at your house right now.
Right, thank you. I copied it.
Okay. I can understand that being a wee bit confusing, guys. So let me show you a cartoon that I think will help a lot. Okay. Where are we here? Okay, so here we go. I want you guys to consider a long platform in space. And because this is black and white, they have a flash bulb going off at position A and a flash bulb going off at position B. And two photons are traveling towards the observer at the speed of light. Meanwhile, there's a dude down here who's traveling past on his magic skate shoes at some high percentage of the speed of light. Now, notice that from the observer on the platform's position, both the photon fired at A and the photon fired at B reach him at the same time. His interpretation of the event is that these flash bulbs have gone off simultaneously because he will see the light from the flash bulbs at the same time. Does that make sense so far? Okay. Imagine that he put two sensitive CCD detectors on each side of his body that would record the photons. Those detectors would get the photons at the same time. According to the first postulate of special relativity, the laws of physics behave the same in all inertial reference frames. This implies that not only will this observer detect the flash bulbs at the same time, it also implies that the moving observer must agree that the two photons strike him at the same time, because they could go and check his CCD log later and see that it happens that way. Unfortunately, from his point of view, if all photons travel at the speed of light and he's zipping past at a really high velocity, the events can no longer appear simultaneous if he wants from his point of view, if he wants both photons to hit the observer at the same time. And here I want you to watch. From the observers on the ground's point of view, they can argue that they are at rest, according to the relativity principle, and that the platform is moving past him at some high percentage of the speed of light. If he agrees that all photons travel at c, he requires the A flash to go off before the B flash so that the A flash has time to catch up to the person in the middle of the train. In other words, if you're on the platform, the events appear simultaneous. But if you're on the ground, the events occur in sequence, A flash first, B flash second. This is the concept meant by the failure of simultaneity. I hope that helped. I'm sure you've got some questions. We'll try a sample problem with it during our homework today, okay? All right. Let me get into some of the last two consequences of special relativity. I don't have time to derive it for you, although the book does attempt a derivation. Have you guys ever heard of this equation before? I bet you have. E equals mc squared was first derived by Einstein while trying to make calculations in relativity. He kept attempting to calculate the kinetic energy of a moving particle at relativistic speeds, and he kept coming up with this leftover term mc squared, which was left behind even when the particle's velocity was zero. Einstein interpreted this term as a form of energy inherent to the mass of the particle itself. In a way, since the speed of light is a constant, he's actually claiming that mass and energy are the same concept. Okay, that's pretty weird because if you remember our basic physics lessons, mass started out as the amount of stuff that's in stuff, or something I wouldn't want dropped on my head, right? And energy was like this abstract gossamer thing that happens when you fight against a force field. Somehow those two things are the same, and I'm not sure anyone on Earth is 100% comfortable with that, okay? We refer to this mass as the rest mass or the rest energy. In fact, when you study relativity proper in a formal classroom, they do not measure energy in joules. They measure energy in kilograms. It's pretty darn weird. One last consequence of special relativity. I would love to talk more about that. I don't have time. It turns out that if times become dilated as you move at high velocities, and if lengths become contracted, it turns out that there's a relationship between distance and time in relativity. Now, you guys remember that we learned about the Pythagorean theorem. Okay, I'm going to actually need to erase for this, for my last consequence, okay? Can I erase this stuff? I want to introduce the final consequence of special relativity, a four-dimensional space-time. Relativity connects the three coordinates of space, up, down, left, right, forward, back, to the dimension of time. Remember that in 2 dimensions, your Pythagorean theorem, x squared plus y squared equals s squared. We worked with that during our lab this week, remember? Do you guys know that there is a 3-dimensional version of the Pythagorean theorem? X squared plus y squared plus z squared equals s squared. What I had in mind someday for a lab is I actually want to create a vector machine for students. I would take a meter stick and I would build a box 1 meter tall, 1 meter long, and 1 meter deep. And then I plan to put a dowel on a rotating pivot point in the center where we can slide that dowel into the box. We could calculate the length and see what its components were in the x, y, and z dimension. If you do this, you will discover that the Pythagorean theorem holds in 3D. A 3-dimensional dowel inside of a box will have the square of its length equal to the square of its x, y, and z components. There is a 4D version of the Pythagorean theorem. But did you guys see how when I traveled at the speed of light in my van, the time from my house to CCRI became 0 seconds. You would also discover if you plugged the gamma of infinity into length contraction, as Vladimir suggested earlier in our lecture, the distance from my house to CCRI under length contraction would also collapse to 0 meters at the speed of light. And this suggests that there's a kind of opposing force between length and time. The 4-dimensional version of space-time is a little weirder than this, and it's what's known as the space-time metric, okay? The space-time metric is basically a path or a distance in 4D space-time. And depending on which book you read, it often looks something like this. S squared equals x squared plus y squared plus z squared, wait for it, minus the speed of light times the time squared. This is a normal 3-dimensional path through space. This is the distance equals rate times time, the distance traveled by a photon in some interval of time. What's so weird about the space-time metric is that there's a minus sign there. It's often said that photons, things that travel at the speed of light, always have a 0 or null metric. They are kind of instantaneously everywhere in the universe at the same time. Only when you do not travel at the speed of light do time and length oppose each other. Sometimes people try to represent 4D spacetime with these kind of cute diagrams. They're called spacetime diagrams. And I really have to show you one because they kind of just get a little bit wee-woo, a little bit bizarre and kind of abstract and philosophical. When people plot positions in space-time, they make these goofy diagrams called space-time diagrams. And we might actually try making one on the board. In a space-time diagram, you plot distance on the x-axis. So this is sort of distance in space, forward and back. And they plot time on the y-axis. In fact, my mouse is acting funny, and I don't like this picture. So let's try to do it ourselves. Just bear with me here, okay? Introducing a space-time diagram. Let's say you're sitting at a couch playing some video games. And I'm going to put your couch at the origin of my graph. On this axis, I'll plot time, maybe in seconds or something. And since I can only draw one dimension cleanly on the board, this will be the distance from your couch, say towards CCRI or away from CCRI. If I choose my axes appropriately, I can make it such that the speed of light is a diagonal in the middle of this diagram. Allow me to use a dashed line to represent the speed of light.
Because it's what? Is it supposed to be 3D?
You can do it in 3D, but we're just doing it in 2D right now.
I mean, but is it supposed to?
Say that again, Vladimir?
Is it supposed to be 3D? Like, is that the reason why you do the dashed line?
No, that doesn't make sense to me. The dashed line just means that I chose this such that if this is 3 times 10 to the 8 meters. Oh, this, by the way, this is distance on this axis, right? If this is 3 times 10 to the 8 meters, that is 1 second. It's not about 3D versus 2D, Vladimir. It's about me choosing my distance metric such that.
Oh, gotcha.
So this is the speed of light here, okay? Velocity equals c. When you plot your path through space-time, when you plot your path in space-time, it's called your world line, and you make a line somewhere on this diagram. Mariah, let's have you give it a shot. I don't know if you're following me or not, but probably not, but let's try it anyways.
I am.
Okay. Now, Mariah, this is me on my couch. And let's say Mariah is playing video games on her couch, somewhere between me and CCRI. That blue dot represents Mariah. Mariah, if you sit on the couch and you don't move for hours at a time, what would your path through space-time look like? Can you tell me that? You're just sitting on your couch, you're not moving forward or backwards, but time, of course, is flowing while you fritter away your day playing.
Would it look like this way on the graph?
That's right. The world line of a person who does not move is a vertical line. For instance, Mariah, if I sat on my couch playing video games, my world line would be a vertical line along the time axis. I'm not moving forward or backwards, I'm stationary. In a way, Mariah, we have learned that no one can travel faster than the speed of light, correct? Even if I did start to move from my couch, let's say I got on my bicycle and I rode to the sandwich shop, I might be able to bike pretty fast, but there's no way, according to the laws of physics, that I could bike faster than the speed of light. So as I went from 0 meters per second up towards the speed of light, the distance I could travel in some interval of time would always be bound by these dotted lines. That means I could never reach a place that was outside my so-called light cone. All right, here's where shit's going to start to get weird. We call everything within your light cone forwards in time your future. Everything backwards in time from your current position is known as your past. But your past only exists within the light cone. There are areas of space-time outside of your future and past of which you may have no knowledge of. And this is what is known as the elsewhere. There are all kinds of space-time events that happen within your elsewhere. Could I give you an example?
So Mariah is in the area which is considered elsewhere for you.
In a way, and that's because even though Mariah might only be a few houses down from me, I cannot instantaneously send her a message faster than the speed of light. If I called her on my cell phone transmits radio waves which travel at the speed of light. So I pick up my phone, I hit dial, and I fire some photons at the speed of light towards Mariah. When she gets the signal, she will enter into my future here. She's still at her house, but now she's at a point in time forward, which the time lag allowed for the phones to reach her. But could I instantaneously communicate with Mariah in my mind faster than the speed of light? No, I cannot.
Now she enters. Okay, I get it now.
Does that make sense?
Yeah.
For instance, Vladimir, let's just make a much simpler example. And I feel kind of bad because I'm really screwing over the GR portion of this class. Maybe I'll take a little bit of next lecture to do that as well. Let's consider the great star Betelgeuse. That's the red star in the upper left shoulder of Orion. You've probably forgotten this tidbit, but Betelgeuse is located 600 light years from Earth. That means it takes 600 years for these red photons to reach my eyeball when I look up at the sky at night. Because Betelgeuse is a supergiant red star, we know that it is currently on the verge of undergoing a dramatic supernova event. And when Betelgeuse explodes, we expect its magnitude to technically drop because it's going to get brighter. It's going to get so bright that we expect to be able to see Betelgeuse during the daytime. And I believe the brightness of Betelgeuse when it supernovas will be approximately that of the full moon for about a month or two. So if Betelgeuse were to go supernova tomorrow, you'd know it was happening because suddenly you'd look up on the sky during the day and there'd be this fucked up glowing thing there and everyone's going to really, really freak out, okay? Except Betelgeuse is currently in our elsewhere. Vladimir, If Betelgeuse went supernova tomorrow, when would we see the flash?
6 centuries later.
6 centuries from now, and we'd all be dead. So we wouldn't actually get to see it.
So
Because Loki, I want to see that. Tegan, Loki, I want to see that too. Okay. It'd be a good day for astronomers. I should start packing up some Betelgeuse observation kits and sell them for $19.99. Okay, make $1 million. All right. So, Betelgeuse technically is in our elsewhere. The light that we get from Betelgeuse at night is stale by 600 years because it took time to get to us.
so
And
you've no idea what happens somewhere until the photons from that somewhere reach that diagonal and interfere with your timeline.
And the technical term for this in astronomy is look back time. We don't consider the look back time between us and Betelgeuse to be too significant because stars don't change much over 100-year periods. The look back time between us and galaxies, especially galaxies far out there, can be quite significant. That's a problem we have to grapple with in astronomy. It also is something we can use to our advantage because we can see the universe in earlier and earlier states by looking deeper into space.
So I read somewhere that if aliens were, what is this, 265 million years, they would see dinosaurs.
Yeah, totally, right? That's another interesting idea about looking for extraterrestrial life is it takes time for life to develop from a slime pond into Mick Jagger, right? So we have to hope that we are catching, and then you know what comes after Mick Jagger? Nuclear bombs and self-destruction and climate change. So we have to hope that we can catch these aliens at the right point in their civilization where they're smart enough to talk back to us, but not so smart that they either blow themselves up or turn into cyborgs or gray goo or something. Okay, Mariah, go eat that barbecue. Now, Mariah, we're going to start our homework here, so you're going to have to catch up on that later, okay? But
Yeah, I'm gonna probably be back for the homework. I'll probably come right after the break.
yeah, so I'm sorry I didn't quite get to GR today, but I'll squeeze it in somewhere else. Let's take that break. Why don't we give Mariah 20 minutes for that barbecue? So it's 1:30 now. At 1:50, we'll get to it. Does that sound good? All right, I'll see you then. Okay, welcome back. It's time for homework number 9, where we're going to be doing homework problems from chapter S2, S3, and S4. If you're watching this recording later and you saw the email today, I accidentally sent out today's email as chapter 11 homework 10. Sorry about that. Andy helped me figure out that it's homework 9 that we're supposed to do today. As I was explaining to the fellow classmates, before I started recording, here's homework 9, and we're going to have problems from chapter S2, one problem from S3, and one from S4. So let's get right, actually, first let's set up our homework page the way that it's customary for us to do. So, hold on. We have our name at the top of the page. Astronomy 1020, never forget. This will be homework number 9. Please label it as such. People out there keep turning in homeworks in the wrong slot. Guess what you get for a grade? 0. You got to do it right, okay? Yeah, Vladimir.
So a quick question about the lecture. You said that mass is a form of energy, right?
Yes.
So when the sun converts hydrogen into energy, what is this energy represented with? Like, what is this pure energy?
So the energy is in the form of gamma rays, but the mass that converted into those gamma rays was once a part of the rest mass of the protons. Now, Vladimir, sometimes I lie to my students because it's easier to tell lies than the truth. And you will remember that in the proton-proton chain, 4 protons come together to make 1 helium nucleus. I used to enjoy lying to my students.
Glued to them. or anti-neutrino.
Yeah, there's some other stuff too, but forget about that. The big picture is 4 hydrogens make 1 helium and some gamma rays, right? What I used to tell my students when I enjoyed telling lies was that imagine you shave a tiny bit of mass off of the protons, and it's that mass shaved off the protons that gets converted into gamma rays. That is a lie, okay? One of the reasons a good pesky student would know it's a lie is because the rest mass of the neutron is actually slightly greater than the rest mass of the proton. So it actually looks like you've gained a little bit of mass going from hydrogens to helium. Okay. The truth, if anyone cares, which probably no one does.
No, I do.
Okay, if I've set it up suspensefully enough, the bringing together of the 4 protons into a helium nucleus releases a tiny bit of potential energy, maybe maybe electrostatic potential energy or nuclear potential energy. I'm not sure where it comes from. It releases potential energy, and that potential energy mass is actually what's converted into gamma rays. In other words, even though a helium nucleus, the 4 particles themselves are slightly more massive than 4 protons, the bringing together of these 4 particles has less energy than the separation of them. One way to think about it, if that sounds confusing, Vladimir, what has more potential energy? A meter stick lifted 2 meters off the ground, or a meter stick that sits on the ground?
Lifted.
Right.
Has
So if
more-
I release this ruler and drop it to the ground, I have to release energy, correct? Think of the 4 protons coming together as being like rulers that are being dropped on the ground. They have more potential energy when separated than when they do brought together. If you're unsatisfied with that, I would like to suggest some light summer reading for you. Kenneth Crane's Introductory to Nuclear Physics, okay?
That's
Bring that.
quite a light reading, huh?
Yeah, exactly. Just you and your beach bottoms there, you know, sipping the Mai Tai, reading some nuclear physics. Actually, bold styles, right? Bold styles. All right. Let's try our first problem. Wait, chapter S2, can you guys read them off to me here?
S2 47, 51, 53.
S3?
59 and S4 52.
Okay, Mateus, are you down to do chapter S2 47 for us?
Yeah.
All right, what's the title?
1 second. All right, so it is relativity of simultaneity.
What?
Consider the situation in thought experiment 8 about the green and red flashes of light at opposite ends of Al's spaceship. Suppose your friend Jackie is traveling in a spaceship in the opposite direction of Al or A1? Maybe it's A1.
It's Al. Here.
Oh, okay, Al. Sorry.
Mateus?
Yes.
Mateus, I want you to pause for a second because none of this is going to make any sense until we draw a picture, okay?
Oh, got it.
Pause and draw a picture with me, guys. This is from the book. It's Thought Experiment number 8. And there are 3 rectangular spaceships, okay? The first, on the top, is Al's. The second is yours. And there's a third spaceship in this problem, which contains an observer called Jackie. I want to be very clear that Al's spaceship, and only Al's, has 2 blinky lights attached to it. I believe, let me see if I get this right. The green flash is on the right side of Al's spaceship. The red flash is on the left-hand side of Al's spaceship. Since Al sits in the center of the ship, please be aware that it will take time for photons to reach Al for photons to reach you and for photons to reach Jackie. It will also take time for green photons to reach Al, for green photons to reach you, and for green photons to reach Jackie. The only other thing they tell us about this problem, well, okay, in the picture, since we are you is the observer, Al is moving to the right at, say, 90% the speed of light. Jackie is moving to the left relative to you at 90% the speed of light. One of the givens or the conditions of this problem is at the exact moment when all three spaceships are in alignment, you see the two flash bulbs simultaneously burst. Okay, you see the two bulbs go off simultaneous. So you see simultaneous flashes at the exact moment of alignment. Once everyone has drawn this picture with everything that I've had there, then we can listen to Mateus's question or spiel.
Should I read the rest?
Yeah, go for it.
All right, so Al, spaceship, suppose your friend Jackie is traveling in a spaceship in the opposite direction from Al. Further imagine that she is also precisely aligned with you and Al at the instant the two flashes of light occur in your reference frame. Wait, is there another page to this? Yes, A. According to Jackie, is Al illuminated first by the green flash or the red flash? Explain.
Okay, I want to be really clear about what this question is saying. It says, according to Jackie, you got to listen to the words very carefully. According to Jackie, is Al illuminated by the red flash or the green flash first? What do you guys think? What does this setup look like from the perspective of Jackie?
Jackie's the observer of Al.
Yes. And what is Al doing relative to Jackie? Okay.
They're like that.
I think Jackie's going to see the green light first.
Wait, is Jackie going to see the green light? If the question is not asking which light does Jackie see first, the question is saying, according to Jackie, which bulb, which photons will strike Al first? Do you see? Do you want to try to answer it?
I think red.
No, I believe it's blue. The green or the green one.
The green one. I don't want to destroy my drawing there. So let me go to share screen whiteboard and let me show you what the key idea here is. Let me get my box out, okay? Here are our three spaceships in alignment. If you think about it from Jackie's point of view, remember that according to the relativity principle, Jackie's just going to assume that she's at rest because she constitutes an inertial reference frame and there are no accelerations in her frame. Relative to Jackie, you are moving to the right at 90% the speed of light because that's how fast she was going relative to you. According to Jackie, Al should be even moving faster to the right than 90%. It turns out that you have to have a new, I didn't tell you another one of the consequences of relativity, sorry. Velocity addition becomes more complex. It's like you have to add 0.9 plus 0.9, but then divide it by a boost factor. So probably Al is traveling at something like 98% the speed of light relative to her. Who cares what the number is? Both you and Al move to the right relative to Jackie, with Al moving just a tiny bit faster. So far, so good? Now, we knew that you saw the flash bulbs simultaneous, meaning somehow from your point of view, the two flash bulbs hit you at the same time. Let's now think about what Al would see from your frame. From your frame, Al's moving to the right, and the flash bulbs have to hit him at the same time. The only way that can happen, oh, sorry. The flash bulbs have to hit you at the same time. They do not have to hit Al at the same time. That's a key idea in the failure of simultaneity. In fact, if Al is in the middle of the ship, right? If you're seeing the two flash bulbs hit at the same time, but Al has already moved to the right, which bulb will Al see flash first?
The red one.
False. The green one. The reason why is this, Vladimir. You and Al are in alignment. Al's traveling really fast to the right of you, right? The photons, boop, boop, hit you at the same time. But while the photons hit you at the same time, Al rushes forwards. If from your perspective, the bulbs hit at the same time, while Al is rushing forward, he's going to barrel into the green flash first before the red flash has time to catch up to him. From Al's perspective, he'll consider himself to be at rest, and he'll just interpret the event as green flashed first, red flashed second. That's the only way they could hit you at the same time, since you were moving towards the red. The idea is that Jackie is in a similar situation to you. And if the laws of physics are the same in all inertial reference frames, all observers, Al, you, and Jackie, all have to agree that green photons hit Al first. You do not have to agree on the order of events. According to Jackie, Al will be illuminated by the green flash first because he's moving towards the green. A little bit tricky, okay? Al sees, let's color code it, green first. Let's see if we can do any better for the second one. Mateus, give us part B.
Right. So according to you, which flash illuminates Jackie first and why?
So this question says, according to you, which flash illuminates Jackie first? Class?
Would it be red?
That's right. If you see the photons hit simultaneous while Jackie is moving towards the red, she has to barrel into the red photons before the green have time to catch up to her. So the answer to B is Jackie sees red first. Okay. Get that down.
All right. And letter C, according to Jackie, which flash occurs first? Explain. How does Jackie's view of the order of the flashes compare to your view to Al's view?
All right. Can I erase these two? Because I need a little bit of room here. Part C actually has 3 secret questions in one.
Wait, can you?
Huh?
What's the question again?
Yeah.
According to Jackie, which bulb illuminates first?
Which flash occurs first? Explain. And how does Jackie's view of the order of the flashes compare to your view of Al's view?
So what they want is they want you to do Al's view and contrast it to your view of the order of events and compare it to Jackie's. They worded it like dog shit because they probably had some half asleep graduate student write these questions, okay? But what they were trying to get you to do is compare all three all three views of the order of events. So let's go through them one at a time. According to Al, which flash occurs first?
Green.
So it goes green, then red. Let's have some fun. Let's do some pretty colors today. How about your view?
Simultaneously.
Yeah.
You're getting really fancy there.
Yeah. Well, I got to entertain someone, and at least I'll entertain me. Okay. And how about Jackie?
Red first.
As lame as this question is, it kind of perfectly, dare I say, illuminates the essence of the relativity of simultaneity.
So I understood exactly why I thought of this problem wrong.
Okay.
Uh, so the reason why is because I imagined the bulbs to be like, you know how the tennis balls can be shot from a cannon?
Yep.
So this is a wrong concept to think about because you obviously see the tennis ball being shot and then it hits you, but it's not how the light works, because the moment that bulb shoots, you cannot see it. The only time you see it shooting is when it reaches you.
That's the essence of this. The photons finally get to you at the same time, and that's when your eyes detect the flashes.
So the moment I realized that the tennis ball cannon is a wrong concept, I kind of understood why.
And why is because when you see the cannon being fired, because you're so close to the cannon relative to the speed of light, it's pretty much instantaneous, right? But there
the
is
time
no,
to reach me.
yeah, there is no instantaneous. Information takes time to go from point A to point B. Okay, have you guys got this? Because I'd like to erase and move on. Today's homework is not going to be too bad, okay? Okay. Mateus, we're going to need to double up a bit. So why don't you read us another one? Read us 51.
All right, let me just check to see if it's on the same page. Yeah, it is. Okay. So length contraction. Marta has a spaceship that measures 50 meters from end to end when at rest. If she flies past you at 0.75 c, how long will you measure it to be?
Our velocity is 75% the speed of light, clearly within the relativistic regime. What was the rest length of the ship again? My lovelies?
50 meters.
Okay. That means from Marta's perspective, who is in the same frame as the ship, the rest length is 50 meters. Class, what do you say we work this problem by calculating the boost? Does that sound good? All right. The boost, gamma, is 1 over radical 1 minus 75% squared. I want to assume that you guys can handle this now, so why don't you punch that up for me?
Is it 1.5?
I'm sorry?
1.5?
Sounds reasonable. Can someone else confirm that? All right. Now let's deploy the length contraction formula. The observer length is the rest length divided by the gamma, right? That basically means 3/2. What, was it exactly 1.5 or was it rounded to 1.5?
It was rounded. It's 1.5 and then 1185. Do you need more significant figures?
No, that's good. Punch that in then.
Uh, 33.3.
Perfect. Mateus, was that a part A or was that the whole damn problem?
I think that was part A.
Let's all label it as such.
Yes, it was part A. And part B is the star Sirius is 8.6 light years from Earth in our Earth-based reference frame. Suppose you traveled from Earth to Sirius at 0.92 light years. During your trip, how far would you measure the distance from Earth to Sirius to be?
Okay, can I erase this, everyone, so I can set up that problem? Tegan, you cool? All right.
By the way, are we going to go over relativistic addition of velocities?
I have a slide on it, Vladimir. And oops. I don't think so, but since you're curious, I just want to show you something real quick here. Just because you asked about it, and I think it might be kind of interesting to you. This really quick, I'll just put it up on the slideshow. This is how relativistic velocity addition works. Function F5 39. The way the problem would work, it looks pretty similar. In the problem that we just had where there was Bob and Jackie both traveling at 90% the speed of light, what you would do is you would, instead of doing, the Galilean transformation would be 0.9 plus 0.9, and then you would just be greater than the speed of light, 1.8, right? But what you do now is you divide it by this term, 1 plus the product of the two velocities over c squared. So I guessed the answer was going to be 98%. Let's see how well I did. If you added two observers at 90% the speed of light, it would be 0.9 plus 0.9 divided by, open parentheses, 1 plus, wait, was it 1? Yeah, 1
Yeah,
plus.
it was 1 plus.
0.9 times 0.9, so 0.9 squared, close parentheses, equals. Oh, shit, I messed that up.
No, there was a over c squared term.
Right, but c squared is 1 here because it's 90% the speed of light, right? What the crap is wrong with me, guys?
Yeah, it's 0.92 speed of light. The letter B, right?
Yeah, so 0.9, let me try that again, plus 0.9. We know that's going to equal 1.8. Now we divide it by, open parentheses, 1 plus 0.9 squared, close parentheses, and then equals 99% the speed of light. That time I did it correctly. So in other words, to satisfy your curiosity, if you add 0.9 and 0.9c, they add to 0.99c, almost close to the speed of light, right? You can never go past the speed of light. That's the idea. And that is the relativistic velocity addition. All right, back to the problem. Here's Earth. Here's the star Sirius. That's the brightest star in the sky, the dog star at the foot of Orion. The distance between Earth and Sirius is 8.6 light years. They imagined that a rocket is going to travel from Earth to Sirius. Was it 92% in the problem, Mateus?
Yes, 0.92.
Okay. The key concept here is imagine that Earth and Sirius had a long curtain rod stretched from the planet to the star. if you think about it, ignoring the proper motions of the star and Earth itself, if they were fixed points in space, the Earth, Sirius, and the distance in between constitute one inertial reference frame. The observer who's in the spaceship at 92% the speed of light will be traveling relative to this frame. So in a way, let's use colors for this, okay? And we'll use the same colors that we did in our problem last time. This frame here, this entire frame, this is the A observer's frame, right? And this frame here, the rocket ship, constitutes the B frame. What do they want us to do? They want us to find out, obviously, if the rocket B moves past this long curtain rod, the curtain rod and the distance from Earth to Sirius will experience a type of length contraction where the distance to the star actually shrinks. Let's calculate our boost, because that's always a nice thing to do. The boost is 1 over radical 1 minus 0.92 squared. Punch that up quick. The boost, of course, is your whack factor.
2.55.
Okay. So, can someone else confirm that? Just we have, okay, good. The distance observed will be the rest length between the stars divided by the boost. We can use light years because we can use whatever units we want. What do you get there?
Um, 3.4.
Units?
Light years.
Vladimir, what's the implication of this problem?
From the perspective of the person inside the spaceship, the distance between Earth and Sirius is 3.4 light years.
Shrunken. In
Yeah.
other words, Vladimir, if we could ever build spaceships that could get damn close to the speed of light, it would effectively contract the distance that we had to travel to the stars.
So would we conserve fuel?
Yes, well,
I mean, I don't really know what fuel.
it would cost you a hell of a lot of fuel and energy to get to 92% the speed of light. Once you're at the speed of light, there's no friction in space, so you just keep you coast, right?
Oh yeah, that's right. But then, but the mass of the spaceship doesn't matter, right? Because it's space, there's no like
The mass
serious.
does matter.
Yeah, but then
According to
the mass
Newton's
increases.
law, force equals mass times acceleration. The force is the thrust of the rocket engine. That's the mass of the rocket, and that's the rocket's acceleration, correct? In order to accelerate a rocket, your force is being reduced by the mass of the rocket. But there's a problem, Vladimir. As
The mass increases.
mass
Right.
increase, right? As you get closer and closer to the speed of light, it would technically require an infinite amount of energy to accelerate you there. This is another reason why we believe you could not probably actually hit C itself. But in theory, you could get arbitrarily close to it with a sufficient amount of fuel or energy or something. But it would be a pain in the mass, shall we say.
So how can mass actually increase? Because like if you're hit with a ball at a high speed, you just feel that oomph coming from the ball coming to rest.
My only answer is ask a proton in the Large Hadron Collider. That's all I got for you, okay? It is weird. Relativity is weird.
It's not the kinetic energy that increases, it's the mass itself.
The kinetic energy does as well. I'm going to erase this. Do you guys have this? All right. All questions will be answered in good time, Vladimir. I'm thinking applied physics is looking, I'm sorry, applied math is looking a lot less sexy than physics these days. You might be missing your calling. All right. Okay. Let's go on to 53. Mariah, are you down to read that for us?
Yeah, it's time dilation with subatomic particles.
Okay.
Oh, it's kind of
The name of that particle that you're scratching your head over, it's called a pi meson. Okay.
okay. A pi meson. Where'd it go? A pi meson produced at rest has a lifetime of 18 nanoseconds, and then it has in parentheses 1.8 times 10 to the negative.
Totally pointless because we can just work in nanoseconds.
Perfect with me. Suppose a pi Manson, I forgot Manson. Meson is produced in a particle accelerator at a speed of 0.998 light years. No, speed of light. How long would scientists see the particle last before it decays? Briefly explain how an experiment like this helps verify the special theory of relativity.
Okay. So here's my Large Hadron Collider tube. Okay. And the scientist has accelerated the pi meson. What was the velocity again? Mariah, the velocity?
Yes, it's 0.998 c.
Which is actually a lot slower than they actually accelerate them to in the Large Hadron Collider, if you think about it. The rest time of 18 nanoseconds means if the observer and the pi meson are at rest in the same frame, the pi meson will spontaneously decay and disintegrate after 18 nanoseconds. Most of these crazy subnuclear particles have a decay time where they'll pop and they'll turn into something else like gamma rays.
So the principle here is that moving clocks run slow.
Right. But remember, from the pi meson's perspective, 18 nanoseconds is the time inside the van frame. 18 nanoseconds is the rest time, because if you're skateboarding on a pi meson, okay, if you're taking a ride on a pi meson, you're actually inside the moving train car or you're inside the van. Does that make sense? This is the observer on the platform. In other words, the pi meson is B. This is observer A, to use our early language, okay? Let's start by calculating the boost, and then we'll worry about what is what. The boost is 1 divided by the square root of 1 minus 0.998 squared.
Wait, so the scientist will see it for even a shorter amount of time?
Moving clocks run slow. Let's let the math tell us what will happen.
Okay. Oh, all right, that's 15.82.
We'll just go with 15.8. That's all we need. Does the boost have any units?
No, it's just a quantity.
Yep, it's a whack factor. It's a fraction by which times are, or a factor. Oh, is that a bird? Wait, was that a cat? Oh, it's a dog. Tegan, what is that? Tell me about your organism.
This is the dog.
No,
What's-
it's a bird.
That is a cute as hell dog. What's the name of that dog?
His name is Nugget.
Nugget.
That's totally a bird.
Nugget in the house. What do you think about pi mesons, Nugget? Okay. Now let's look at our time dilation formula. The observed time is gamma times the rest time. Where do we want to put in the 18 nanoseconds? Observer time or rest time?
Rest.
Yeah, that's the frame of the pi meson's decay time. We can work in nanoseconds because T and T rest have the same units. What do you get?
284.4 nanoseconds.
Sorry, 3 sig figs, Vladimir.
284 nanoseconds.
So no, the observer doesn't see the particle shorter. The particle actually lives for a longer period of time.
So I confused it because I thought, well, if I'm on Pi Meson, right, and I look at the clocks of the observer, his clocks have to run even slower than mine. So that's why I thought
Right.
that.
In fact, you want to know what's weird? From the Pi Meson's frame, when he decays in 18 nanoseconds, he will see that from the Pi Meson's frame, A's clock will actually be shorter by a factor.
Yeah,
of
that's
16.
why I got it wrong.
During the 18 nanoseconds, the Pi Meson will believe only 1.1 second has elapsed in the A frame. But there's another part to this question, Mariah. What was the second little bit to this?
It says, how long will scientists see the particle last before it decays? Briefly explain how an experiment like this helps verify the special theory of relativity.
Right, because everyone always wants to know, is this shit real or are you just making it up? How would such an experiment help us confirm that relativity is really going on?
Well, the math shows us that there is actual time dilation going on.
The math is the theory. Now we want to think like an experimentalist, Vladimir. If I'm an experimentalist, I can create a Pi Meson in some kind of a particle accelerator or some kind of a vacuum chamber, and I can observe the Pi Meson decay, typically after 18 nanoseconds. Then I perform a second experiment where I put it in a tube and I accelerate the crap out of it with a magnetic field. Because the Pi Meson has such a microscopic mass, it's actually easy to accelerate it to the speed of light with a reasonable magnetic field strength because I'm trying to accelerate such a wimpy little particle. Suddenly I jack it up to 99.8% the speed of light, and instead of seeing it live for only 18 nanoseconds, I actually record its decay time as 284 nanoseconds. I can now demonstrate to planet Earth by publishing a research paper that, look, this thing lives for different lengths of time depending on how fast it's moving. This is actually related to a famous experiment in particle physics that was actually conducted up the street in New Hampshire at Mount Washington. Okay, so the cartoon story, the way it went is, you guys have heard of Mount Washington. Maybe you've even hiked it before, right? It's got some of the harshest weather on Earth. Well, they put a particle detector. Believe it or not, nature has its own version of a particle accelerator. The whole reason we knew about these kind of subnuclear particles is we were finding them and detecting them on mountaintops, because what happens is occasionally stars in our own galaxy or in distant galaxies go supernova, and they eject protons like the solar wind at ridiculously high speeds of 99.999% the speed of light. Those protons then fly through the vacuum of space until they randomly strike Earth. And when they hit the atmosphere of Earth, they have these intense nuclear collisions with diatomic nitrogen or oxygen molecules, and they send what's called a spark shower of wacky particles flying through the air. Now, these scientists in this famous experiment, they set up a particle detector at the top of Mount Washington, and they were getting something like 10 Pi Mesons per day or something like that striking their particle detector. Because the Pi Mesons decay in 18 nanoseconds, they believed it would not be possible to detect any Pi Mesons at the base of the mountain, because by the time they got to the bottom, they would have already decayed. But just for kicks and giggles, they decided to set up a second particle detector at the bottom, and sure enough, they start detecting some number of Pi Mesons. And suddenly they realized, oh shit, what would this problem look like from the Pi Meson's frame? From the pi mesons frame, the mountain had undergone a length contraction, and they could make it to the bottom of the mountain in under 18 nanoseconds. So you can actually look at these problems in terms of length contraction or time dilation. In other words, this showed people that relativity explained why they could still detect particles at the bottom of the mountain. Let's just write a very simple sentence explaining this. Let's say, by observing a high-speed proton, oh, sorry, it's not a proton in this case, it's a pi meson. By observing a high-speed pi meson live 16 times longer than it should, oh man, the sounds of the city are really getting to me today. No, let's leave it open. I want the air. The observer, huh? Oh, okay. By observing a high-speed pi meson live 16 times longer than it should, the observations, we don't want to say prove special relativity, because you can never really prove a thing in science. You can only disprove it. The observations support the theory of special relativity. They add support. Underline the word support. That's a key term. The observations support the theory. I'm going to abbreviate special relativity as SR because I'm feeling a little lazy.
So far, nothing has disproved this theory of special and general relativity, right?
Correct. And that's why it's considered a theory. A theory is the highest status a scientific concept can have. Relativity has been tested like tens and tens of thousands of times by so many different experiments looking to find some contradiction in it. And what's spooky is relativity is always held up under scrutiny to this date. There are a few strange things. Dark matter and dark energy have potentially challenged it, or we don't know what can explain those two things. And some people have suggested maybe we need to modify relativity in some way. But so far, none of the modifications have found any actual observational support. So far, relativity is golden. All right, I'm going to erase. We're going to move right along.
What's the word before support?
Observations.
Oh, okay. Thank you.
Sorry about that. Can I erase everyone? Mariah, I'm going to have you read again because Vladimir doesn't have his papers here today. So can you do 59 for us as well?
Yeah, it's gravitational time dilation on Earth. For relatively weak gravitational fields such as that of the planet or an ordinary star, the following formula tells us the fractional amount of gravitational time dilation at a distance r from the center of an object of a mass object, or of a mass m object.
I believe, Mariah, it's 1 over c squared times g. Help me out with the rest of it.
M object over r.
Okay, before you continue, let's draw a picture here. Here's your planet or star, which has radius r, but we're going to be comparing a clock at the surface of the planet or star with a clock out in deep space, some coordinate value r from the center of the star. Let's call this one the space clock. That's the clock that's far from the gravitational field. And let's call this one the I don't know, let's call it the star clock or the planet clock. It's the surface clock, okay? Now, we didn't quite get to general relativity today. But let me tell you, without evidence or support, that general relativity has a whole bunch of consequences that are somewhat similar to special relativity, but they depend upon gravity instead of velocity. One of the funnest and one of the ones used in science fiction movies like Interstellar, if you guys ever saw Interstellar, is an effect known as gravitational time dilation. And here's the formula for it. The idea behind gravitational time dilation is that clocks will run slow at the surface of a highly compact, both massive and compact planet or star, relative to a clock that's out in deep space far away from it. So clocks run slower in the presence of a steep gravitational field. What we see is an equation that looks exactly like time dilation, except instead of v squared over c squared, it's this term over c squared. You guys have seen that term before. Do you know what it is? 2gm over r? That term is the square of the escape velocity. When you guys had to do escape velocity calculations, it was the square root of 2gm over r. So basically what you've done is you replaced the velocity from special relativity with the escape velocity, and that's your new boost. Pretty wild, huh? Okay. Mariah, can you return to the problem and read us what's up here? So you last said that this calculates the fractional amount of time dilation.
For example, while 1 hour passes in a deep space far from the object, the amount of time that passes at a distance r is 1 hour multiplied by the factor above.
That's actually a lie. It took me a while to figure out why things weren't working right in this problem. They lamely said fractional amount of time dilation, which is a little bit vague. What they really meant to say is that this equation is equal to the difference in time divided by the time in deep space, which should not be affected by the gravitational field. Where delta t here, wait a minute, if clocks run slow at the surface of a star, if 1 hour passes in space, should this clock be slightly under an hour or slightly over an hour?
Under.
Under, Mateus. Because remember, it's the rate that the needle is flowing, right? If the space clock flows all the way to 1 hour, the rate of the needle should be going slower. The rate that the hand of the clock moves should be slightly slower. So this clock should be somewhere under an hour. So the fractional time dilation should actually be t space minus t star. That's what the delta t is, divided by the t space. They did not make that clear in the problem. Luckily, you guys have me, and I know what was going on. Okay, what does it want us to do, Mariah?
Calculate the amount of time that passes on Earth's surface while 1 hour passes in deep space.
Okay. The radius of Earth is 6,400 kilometers. All right. Let's plug that and the mass of Earth into our equation. You guys will remember that the mass of Earth is 6 times 10 to the 24 kilograms. So the delta t over t space is 1 over c squared. Remember that c is 3 times 10 to the 8 meters per second square thereof, times big G. Well, we're just going to be lame and use 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass of Earth, 6 times 10 to the 24 kilograms. And we're going to divide it by the radius of Earth in meters. Who can convert 6,400 kilometers into meters in their heads real quick?
6.4 times 10 to the 5.
False.
6.
3 more zeros, right? So it's 6.4 million meters. Okay, I want you to punch that all up. One sig fig will suffice. Nugget. Nuggets punch into the calculator too. I like that. Damn, that's a cute dog.
I have a feeling I screwed up.
What'd you get?
First of all, it's a negative number.
It's a negative number? That's not possible. Those are all positive quantities.
Yeah.
Is it a negative
Oh,
power?
wait. Oh, it's times because I put subtract. Never mind.
Mariah, Mateus, Tegan?
I got 7 to the negative 10.
You mean 7 times 10 to the minus 10. Thank you very much.
Yes, that's what I meant.
Okay, what are the units, Mariah?
Give me a second.
Are you going to go try to balance them out?
Yeah.
Good, I'm proud of you.
But I mean, you're talking about time.
Am I, though?
Oh, you're not?
That's what I'm asking you.
Time dilation.
Why don't you, Vladimir, use it as an exercise in unit balancing and dimensional analysis. Tell me what the units
I'm too lazy. I'm trying to think it out. Okay, all right. There is nothing.
Very good. Very, very good.
I thought I was going crazy. I'm like, everything cancels out. I'm confused.
Because it's a fractional time dilation. Look at units here. Hours minus hours is hours. Hours over hours is nothing, correct? Meters squared, here's another meter to make meters cubed. They cancel. Kilograms cancel, and seconds squared cancel.
Actually, we didn't have to do all of that because you could look at the original, the equal sign. So, yeah, change in time over change in time. It's
a change in time over a time. Yeah, but you didn't do that because you said, Brennan, the units should be units of time. And I said, should they? And then I wanted, but that wasn't obvious to you, okay? All right, we're not done yet. They actually want to know how much time has elapsed on the star clock if 1 hour has passed on the space clock, correct? Let's look at the other side of the equation. T space minus T star divided by T space. Do you guys have the math chops here to solve for T star? Let me help. I'll erase up here.
is it 7 times 10 to the negative 10 times T space?
Okay,
Then
let's make this easier, Vladimir.
okay.
Remember that T space, they asked for how long will pass on the surface of the star if 1 hour passes in deep space. If T space is 1 hour and I multiply it up there, I get T space, or 1 hour, minus T star is equal to 7 times 10 to the negative 10 hours. Did you guys follow that jump there, or did I jump too many stones for you? I set that equal to 1 hour, correct? And I multiplied it up here to give me 7 times 10 to the minus 10 hours. Then I took t space minus t star, and I also substituted 1 hour in for there. I'm going to add t star to this side and subtract 7 times 10 to the minus 10 to the other side. That gives me t star is 1 hour minus 7 times 10 to the minus 10 hours. I don't think you can do that in your calculator because your calculator only has 9 or 10 decimal spaces. You guys want to see a trick for how to figure this out?
No, the calculator actually does do it. It's just a bunch of 9.
It didn't do it right. Watch this, guys. It took me a while to figure out how to do this. And I just taught myself this, so I don't know if this is an official math trick or not. I said, okay, my calculator can't handle 7 times 10 to the minus 10, right? What if instead I did 7 times 10 to the minus 3? 1 minus 7 exp negative 3 gives me 0.993. Do you see how the 3 is in the third decimal place? I then suspected that if I did 1 minus 7 times 10 to the minus 4, I would get 0.9993. Let's see if that's how it works. 1 minus 7 exp negative 4. And sure enough, the fourth digit was a 3, right? That suggests to me, if I do 1 hour minus 7 times 10 to the minus 10, I will end up with 0.999999993 hours. Did you see how I did that? I used tricks and analogies to prove to myself that the 10th decimal should be a 3. And that's how long a clock will run on Earth. Is that a lot of gravitational time dilation?
Nah.
Now,
It's
because
significant.
Earth has a weak-ass gravitational field. And yet, Vladimir, it is possible for us to measure times to that level of precision. I've got something to tell you. Shit, where's my laser? Hold on, guys. Oh, it's in my pocket. You guys see these things? You know how like Zuckerberg can track your location and you have like a compass app in here? I actually know my location on Earth down to the arc-second precision, both in latitude and longitude. Today, we use gravitational time dilation and the theory of general relativity to pinpoint and geolocate our cell phones on Earth. Satellites, communication satellites up in orbit, use the microscopic fractional amount of time dilation between your location on Earth and the satellite to get super high precision estimates of your latitude and longitude. And today, everyone's cell phone is using GR for that purpose. Something that seems like this totally wacky abstract theory of physics has some funny and quite practical applications. Don't say Einstein never did nothing for you, okay? One problem left to go and then we're done. You ready? Okay. Mateus, Tegan, you tried to get, do you have the problems handy or are you outside?
I did. I had them open on my computer, but I have to be on my phone now because I can't use the internet on my laptop right now.
That's fine. It's a sunny day, so you should be outside. Mateus, you down to give us that last one?
Sure.
That's S452.
All right, so gravity and the EM force.
I'm going to call it gravity versus electromagnetism.
Okay. In this problem, we compared the strength of gravity to the strength of the electromagnetic force for two interacting electrons. Because both electrons are negatively charged, they repel each other through the EM force. Because electrons have mass, they attract each other through gravity. Let's see which effect will dominate. You will need the following information for this problem. The force law for gravitation is Fg times m1 m2 over d squared.
Okay.
And
so on this
G,
side, I'm going to put gravity, and it's a versus battle. Electromagnetism on the other side. We know the gravitational force law. Big G times m1 times m2 divided by the distance squared. You've seen that before. Now, rather than make Mateus try to read it, by a weird perversity of nature, the electromagnetic force law looks exactly like the gravitational law, but instead of mass, it uses charge, which we use the letter Q for. It also has its own constant. The force of electromagnetism, let's call it big E for electromagnetism, times charge 1 times charge 2 divided by the distance squared. You guys haven't had a course in electricity and magnetism before, so let me tell you that the unit of charge is called the coulomb. We measure static charges in a fancy unit called the coulomb. They should have given us some givens. Mateus, for instance, I think they said, what, 10 to the minus 10 meters was the distance?
even. They didn't really say the distance. They give you the force law for gravitation,
No,
and then where am I? Abbreviation of the force law. I don't see it.
Look, here it is. Part A.
Oh, okay, got it.
Calculate the gravitational force in newtons attracting the two electrons due to gravity if they're at a distance of 10 to the minus 10 meters, okay? By the way, they give us the mass and the charge as well. We should probably write that down, okay? The charge of an electron, I already forgot it, is not negative 1.6 times 10 to the minus 19 coulombs. The electromagnetic force, I think, is 9 times 10 to the 9. Is it newtons per coulomb squared? How do they measure that again? Nine times 10 to the 9. Oh, Newton meters squared per coulomb squared. Damn it. The mass of an electron is 9.1 times 10 to the negative 31 kilograms. Is that right? Yeah. 9.1 times 10 to the minus 31 kilograms. The distance in both problems is 1 times 10 to the negative 10 meters. Look at my drawing. The electrons are at a fixed distance. By the way, that's the same as 1 angstrom. They're 1 angstrom apart, or a tenth of a nanometer apart. We know that they have mass, and therefore they should attract each other a little bit by gravity. We also know that they're two negative charges and should repel each other by electromagnetism. Our goal is to find the value in each case and see which is stronger. Do you guys know which one is going to be stronger, gravity versus electromagnetism?
Electromagnetism is going to clap gravity.
Totally. And if it didn't, you would know it just by holding up two magnets. If the gravitational force between these magnets and Earth was greater than their magnetic force, this gravity would rip these things apart and pull them down. Gravity's clearly not strong enough to do that. Wait till you see just how much stronger EM is. Okay, I need to erase this so I can set up the equations. You guys ready? Do you have all this intel on your page? Okay. I might need you to shout these numbers at me. Okay, part A, gravity first. The force of gravity is 7 times 10 to the negative 11 meters cubed per kilogram per second squared times the mass of an electron, 9.1 times 10 to the negative 31 kilograms, times the other mass of an electron, same mass, 9.1 times 10 to the 31 kilograms, divided by 1 times 10 to the negative 10 meters squared. Why don't you guys punch them up and tell me what you get? One sig fig is fine.
Um, 6 times 10 to the negative 51.
Units?
That sounds reasonable. Newtons.
Yeah, I mean, the masses of electrons are so small that they truly have a pitiful gravitational force. I mean, crap, Vladimir. The masses of these two markers are way more intense than the masses of two electrons, and I still can't even feel the gravitational force between these guys, right? I would expect it to be extremely pitiful for two electrons. B.
Weak ass force.
Weak ass force. It's honestly the truth. Weak AF force, okay? Now let's do electromagnetism. The force of electromagnetism is 9 times 10 to the 9 Newton meters squares per Coulomb squared times, let's just drop the negatives because we're going to multiply two negatives to make a positive. So it's 1.6 times 10 to the minus 19 coulombs times 1.6 times 10 to the minus 19 coulombs. There were negatives in both of those, but they're going to cancel out, so screw it. Divided by 1 times 10 to the minus 10 meters squared. One sig fig is fine.
Wow. 2 times 10 to the negative 8.
Units,
Newtons.
because it's a force. Yeah, wow is right.
So billions of times, even not even billions, trillions, quadrillions, octillions.
Kabillions. One of my former tutors, when numbers got so big that he couldn't remember their names anymore, he would just call it kabillions. So I've adopted that phrase. Kabillions made stupid number of times. In part C, they of course want us to actually calculate it. Do you guys have this down? Tegan, you good? All right. So in part C, Mateus, they just ask us to compare them. The ratio of the force of electromagnetism to the force of gravity is 2 times 10 to the minus 8 newtons over 6 times 10 to the negative 51 newtons. Let's do this in our heads. 2 divided by 6 is 1/3, correct? 1/3 times 10 to the, okay, what is negative 8 plus 51?
43.
43, did we do that right? Yeah. So it's 1/3 times 10 to the 43 I'm pretty sure 1/3 is 0.33, right, Vladimir? So
Yeah.
approximately 3 times 10 to the 42 times. So electricity and magnetism is 42 orders of magnitude stronger than gravity. This is the reason why electricity is so. Hunter S. Thompson once wrote that electricity is mean and it wants to kill you. Electricity is violent because when you do get huge asymmetries in charge, when nature is foolish enough to dabble with such things, that's when you get powerful repercussions. One of which, for instance, is lightning strikes, right? Oh, lightning, that helps. Lightning is an example where you get huge buildups and huge asymmetries of charge. And it's so powerful, electricity and magnetism, that if your clouds build up enough positive charge, it will literally rip electrons off of the ground from Earth and sizzle and heat up oxygen on the path towards neutralizing that positive charge in the clouds. You're literally sucking electrons right off of the ground, and they're traveling with such an intense current through the air that they're heating up oxygen and causing it to glow on its journey through the sky. Planet.
So,
Oh, yeah?
so the actual lightning is not from above to below, but from below down to up.
There are even other rarer forms of lightning that are very infrequently observed except by high altitude pilots. I believe there's a sort of upper lightning. It might even be red in color, where charge flows from clouds, or actually from the upper ionosphere down to clouds. Those types of lightning strikes are very, very rarely seen and only occasionally by high altitude pilots. I think they're called sprites. There are people who are into atmospheric phenomenon. Are they called sprites? Hey, I'll be done in 1 sec. Yeah, wow, they're actually, shoot. I saw a picture of them and now I'm seeing stupid little sticker Care Bears. This is what I'm talking about. Yeah. This type of lightning, I can't even believe there's a photograph of it. Look at that shit. Isn't that crazy? That's like an inverted kind of lightning that goes from cloud tops up to the ionosphere or something. I don't know how much is known about these things. I don't know a ton about them, but I've heard of them before.
So I have another question. Do ball lightnings actually exist, or is it some dubious? Yes.
I think it does, right? Ball lightning, yeah. Yeah. But now that you mention it, I don't really know what it is. Spherical objects, an unexplained phenomenon associated with thunderstorms. I have never seen such a thing. I'd heard of it, but I didn't really know what it is. You just gave me something to Wikipedia read while I eat my little snack today, Vladimir. Thank you.
You're welcome.
I'll be reading about this and we can talk about it later. When I see the term unexplained phenomenon, my usual first thoughts are, okay, so it's bullshit. That's what it is, okay?
Yeah, that's why I was asking you. That's why I was asking you. So is it like made up some like source trust me bro or some actual stuff?
Well, in 2014, scientists from Langzhou, China published the results of recordings made in 2012 of the optical spectrum of what was thought to be ball lightning. It sounds like it might be a thing, but it's well, I don't know. I don't want to start yapping about it until I have a vague sense of what I'm talking about. It doesn't sound like anybody really knows what they're talking about. I'm going to read about it and we'll get back to that, okay? But thanks for giving me something to think about. Okay, guys, we spent another Thursday afternoon together. Like, comment, subscribe. Hopefully enough of you can log in on Tuesday so we can have a good lecture. We might go back to stars for a little bit in fusion, but then we're going to come back to GR later when I get into the death of stars and black holes and neutron stars. So we'll do a little more of this stuff. Somehow I'm going to squeeze in some GR. I'll do it somewhere, okay? We'll just talk about...
Does time stop? Does time stop in black holes? Does time stop in black hole?
Well, it depends which observer you are. If you're an observer looking from the outside, time will sort of stop when you hit the event horizon or the surface of the black hole. If you're falling into the black hole, however, time does not stop. And we will get to that. Those questions will be addressed before the end of this class. All right, guys. Have a great day in the sun. Get outside, get some sunshine, and I'll see you all on Tuesday. Peace out.